Okay, can somebody confirm that you can hear me?
Yes.
Thank
Yes.
you. Before we begin, are there any questions?
I have a quick question, Dr. Volp. This is Katie. Um, just related to the lab worksheets, can you just remind me how many days we have after the first graded worksheet has been returned to us that we have to resubmit the second version or the second attempt?
It'll be a little less than a week. What I do is usually the first grading is done that Saturday of the week. I mean, that's when it's due, I should say. The lab worksheet is turned in Saturday after the lab.
Mhm.
And then I will give you another week to get the second grading done. But obviously, it takes me some time to get the lab graded. I think I got everyone graded by late Tuesday night, so that would be early Wednesday morning or late Tuesday night.
Okay, thank you so much. Got it.
All right. If I don't get it done around that time, I will then go in and change the until date and give you generally more time. Sometimes I make it on Tuesday, but usually I make it a whole week later. Because the second grading, I'm not going to promise when I'll get it graded, but the first grading, I generally try to get it graded shortly after you turned it in, within a few days. Let me state that I have graded Lab 0 and Lab 1. And some of you, I can say, could have used my help. And if you're not doing too well in the lab, you should try and work on the lab while I'm there. And then if you're stuck on a question, you can ask me. I am there in the lab to help you guys. And that's my what's the word? That's the way I am, okay? I consider myself here to help you learn. That's the
Can I
whole
ask one more follow-up question, Dr. Volp? It's Katie again. After the labs have been graded, and apologies if this has already been reviewed, but are we allowed to ask questions on the student discussion forum if we are having any issues with any of the questions that have been that are wrong?
You can ask questions on the student discussion, but realize students are going to be the ones answering that.
Yeah, for sure.
Yeah.
Okay. Thank you.
All right. Um, and by the way, my name is Volpe.
Oh, Volpe. Sorry, Dr. Volpe.
No problem. Yeah. Okay. So today is January 18th, and we are going to be covering chapter 2 today. Let me state that was it yesterday? Yeah, it was yesterday. The network was down at Clark College all the way until something like around 5 p.m. Maybe no, it was more like 7 p.m. It was down all the way until about 7 p.m. And so if you tried going in and doing the quiz, Respondent's Lockdown Browser wasn't going to work. I'm actually surprised you're even able to go into the website and try and get the browser up and running because I couldn't get into Canvas at all until 7 p.m. or after 7 p.m. And so I extended the time that the quiz is due. It's no longer due on Wednesday. It is due today at 11:59 p.m. And you can look at the until date. Canvas always has a due date and an until date. I always use the due date for the first grading of the lab and the until date for the second grading of the lab. Normally, on most assignments, I will have the due date and the until date the same. But on this quiz, because of that problem, I changed the until date. And If you got in after 7 p.m., then you should have had no trouble with Respondus Lockdown Browser. And I don't know when the problem first started, but at least for all of the afternoon, you could not log into Canvas and you could not do much at Clark College. I could not have my my lecture on Monday and Wednesday. So what would that be? Wednesday. So we're going to have to make another schedule for the Monday, Wednesday. And for you guys, I think I'll just leave the schedule the same because you will be following the same schedule. But their schedule is going to have to change because I was not able to lecture on Wednesday. Fortunately, I was able to run the lab. We got started a little late, but it was like 7:12 or 7:15. I was able to log in and get the lab started. All right, any question about any of that? If not, let's begin chapter 2. I've got it up here someplace. There we go. Chapter 2, Chemical Principles. This slide is showing you the major goals and a rough outline. Always know the terms of the chapter. And remember, if you want to know all of the terms, this is only the major terms, you need to look at the overview and objectives. So take a look at the objectives. And that reminds me, I need to open up the slideshow for chapter 1 and chapter 10. But if you want to get all of the goals, the learning goals, come to the overview and the objectives, or maybe I'll call it the study guide and it'll be on top of the study guide. Any question about any of that? Now, while I'm thinking about it, let me open this for the Monday, Wednesday lab. If it isn't open after I finish the lesson, send me an email to remind me to open the slideshow. I just remembered now, so that's why I'm opening it. If you notice, I have a large number of emails. I have not checked my emails today. Hopefully I'll get started on that after I'm done talking in the lab. All right, so with the main outline also with respect to the 4 major biological molecules, be able to describe the relationships and the characteristics of the monomers to the polymers. Of the 4 major biological molecules, they are the 3 main molecules you find on any labeling, like a box of cereal, and they will be carbohydrates, proteins, and lipids. Now, on the box of cereal, they'll call it fats, and we're going to use the term lipid because it's more inclusive. The 4th major biological molecule is not shown, and I've never seen it on any food labeling, and it's nucleic acids. These are the 4 major biological molecules because all living things are made mostly of these. And you only find them in something that is alive or was once alive, meaning of the 4 major biological molecules, you will not find them from rocks from the moon, but you can find them from rocks on the planet Earth. And that's because there will be a fossilized living organisms in the rock, and then that can get the biological molecule into the rock. But those molecules are only found in living things or something that was once alive. And then describe the composition, the structure, and function of the four major biological molecules, and then give examples of each. Any question about any of that? All right. So when we're talking about chemistry, it's important to realize the scale of things. Let me blow this up. So you should know about the biggest thing we'll talk about is a human. Obviously, there are things bigger than a human. And then there will be a chicken egg, which the yolk will be the largest cell you've ever seen. There are a few cells on the planet Earth larger than that, but most people have not seen even the yolk of a turkey egg. And the largest current cell on the planet is the yolk of the ostrich egg. The smallest cell you can probably see about is frog eggs, a little bit smaller than that. We can't see that. You need a light microscope to see most eukaryotic cells. Smaller than that, we have bacteria, most bacteria. Smaller than that, we have viruses. Smaller than that, we have complex molecules like proteins. Smaller than that, we have small molecules like water. Smaller than that, we have atoms. You do not need to know the size of these molecules, but you should, or things, but you should probably know their relative rank. Certainly you should know that atoms are smaller than small molecules, which are smaller than large molecule, like a protein, which are smaller than viruses, which are smaller than prokaryotic cells, like bacteria, which are smaller than eukaryotic cells. So we can see things down to a little bit smaller than a frog egg. Then we have the light microscope, which can see the smallest bacteria. And then we have the electron microscope, which can see most viruses. The only virus, there are a few viruses which you can see with the light microscope, but most viruses you need an electron microscope. Any question about any of that? Let me point out there is an error in this scale. It has 1 micrometer twice, once here and once there. This one should be a millimeter, and I have that corrected in our next slide of this. Not this slide, but the next lesson with this slide. All right, so in chemical principles, it's important to be able to distinguish the biological molecules and separate them from an organic compound and separate them from an inorganic compound. An organic compound is a molecule and it's typically complex structurally. It typically has carbon binding the other atoms together because carbon can bind to 4 different atoms. And it's mostly held together by covalent bonds, covalent chemical bonds. An inorganic compound typically lacks carbon, although there are exceptions. They are required by living organisms to grow, repair themselves for their maintenance and for their reproduction. Some examples of an inorganic compound are carbon dioxide and oxygen gas and water. And water is actually one of the most important and abundant molecules in all living things. Water makes up, let me see, I used to know this, over 70% of living organisms or even a cell. Any question about any of that? We'll talk more about organic compounds a little bit later in this lesson. For the moment, we're going to talk about inorganic compounds, particularly water. Water is a polar molecule. A polar molecule is one that has a partial charge on one end of the molecule and a partially positive charge on the other end. So for water, the oxygen has a partial negative charge and the hydrogens have partially positive charges. This polarity happens because water pulls on the electrons in this covalent bond here stronger than hydrogen. So the electrons in this covalent bond spend more of their time around oxygen than they do around hydrogen, making hydrogen have a partially positive charge and oxygen a partially negative charge. And Tutora doesn't call it a partial charge, he calls it a slight charge. The important part is to realize a polar molecule is not an ionic molecule. An ionic molecule will have a +1 or a +2 or some positive number of charge on one atom, and then a negative complete charge or complete two charges, or etc., some number, complete number on the other atom. And they don't, ionic molecules do not have a covalent bond linking them together. They have an ionic bond. We'll talk a little bit about that. But water is a polar molecule. Because water is a polar molecule, it can form hydrogen bonds. A hydrogen bond is where the negative charge of oxygen on this water molecule will be attracted to the positive charge on the hydrogen of this water molecule. So a hydrogen bond is a chemical bond between different water molecules or between different molecules if the hydrogen bond is happening in a substance other than water. So hydrogen bond happens between different molecules, and it happens because the oxygen of this water has a partial negative charge, and the hydrogen of this water has a partial positive charge. That creates an electrostatic attraction between the positive charge, partial positive charge, and the partially negative charge. Any question about that? So here's a question for you. How many chemical bonds does water, I'm talking about the substance, not one molecule, meaning many molecules of water, how many different chemical covalent bonds does water have?
Two.
Two, at least two. Water has a covalent bond between the hydrogen and the oxygen, and it has a hydrogen bond between the different water molecules, between the partial negative oxygen and the partial positive hydrogen. All right, let's watch a little video on the water molecule. Try and get it to work. Oh, there it goes. It's just slow. Oxygen, hydrogen, the green ones, water, blue and green, hydrogen being the green. A partial positive charge on the hydrogens, partial negative on the oxygen. And there is a hydrogen bond forming between the partial negative oxygen, and the partial positive hydrogen. Any questions about that? If not, I'm going to end that because I think this is all it is. Oh, it does show the water forming a hydrogen bond between this molecule and that molecule, and then this molecule and that molecule, and sometimes between that molecule and that molecule. And then you can have water forming hydrogen bonds with 4 other water molecules. That movie isn't too good. I'll have to take a look and see if that one's a little better, but we'll just end it there. Water is a good solvent because water can dissolve polar molecules as well as ionic molecules. Polar substances dissociate in water, forming solutes. For example, the sodium chloride crystal composed of chloride ions, the yellow ones, and the sodium ions, the positive. Water molecules, let me blow this up, can come in, and the positive, partial positive of water can surround the negatively complete charge of chloride ion. And then different water comes around and pulls that chloride ion out of the crystal. And now we have chloride ions in solution as a solvent. No, as a solute in the solvent. The water's the solvent. And then the same thing with the sodium ion, having a complete positive charge here, the negative charge, partial charge of oxygen in water can surround the sodium ion like this, and then pull that sodium out of solution or out of the crystal and bring it into solution like that. And that's how water can dissolve ionic molecules. These are ionic molecules. And then water can also dissolve polar molecules like water. A polar molecule would be one where the one end of the molecule will be partially positive charged and another end of the molecule will be partially negatively charged. One example of a polar molecule is sugar. Sugar does not have a complete positive charge and a complete negative charge, but it does have regions of it which are polar, where they have a partially negative charge and a partially positive charge. And then sugar would be replacing the screen in here. Let's put it here because it's a little bigger. And then the water will be surrounding it. The difference is that with sugar, water would have the hydrogens wherever the sugar is partially negative, but where the sugar is partially positive, water would then have the oxygen, the partial negative oxygen, attracted to the partial positive sugar, if you understood what I said. Any questions about any of that? There's a little video on how water dissolves salt. I don't think I normally show this, but I can't even click on it, so we'll just move on. But you can grab the link and take a look at the video if you like. So water is a good solvent because it can dissolve polar molecules and ionic molecules. Polar molecules are hydrophilic. Hydrophilic means literally lover of water. Is that right? But what it means is it likes to be around water. Non-polar molecules like oil or butter are hydrophobic. This literally means phobic fear of water. And what it means is that hydrophobic or nonpolar molecules tend to not want to dissolve in water. They tend to stay away from water. And you know that when you're making salad dressing, you take the oil and you take the vinegar and water, and vinegar is mostly water, but it has acetic acid in the water to make the vinegar, and you mix them up and they'll separate because the oil is hydrophobic and the vinegar is hydrophilic. Any question about any of that? So polar and ionic molecules are hydrophilic. Non-polar molecules are hydrophobic. All right, hydrogen bond forms between different water molecules. It is what makes liquid liquid water. I don't know if you can see this. I've got very little water in here, but I got a little bit. Maybe you can see it there. The reason why liquid water is a liquid is because of the hydrogen bonds holding the water molecules together. And these hydrogen bonds break and reform all the time. And that's why it is a liquid. Why the water will take on the shape, I don't know if you can see that, but it can take on the shape of the container because it's a liquid. The hydrogen bonds break and reform, and then the water can take on whatever shape it needs to fill the container. That isn't always the case. Ice, which is water, does not take on the shape of the container. And the reason why ice is a solid is because the temperature of the ice is so low that the temperature cannot break the hydrogen bonds that are holding the water molecules together. And that is why ice is a solid. And then, of course, you can totally break the hydrogen bonds in liquid water, in which case you no longer have liquid water, you'll have gaseous water. And that's because the temperature and energy of the water are so high, they break all of the hydrogen bonds holding the water together, and then we no longer have liquid water. Any question about any of that? All right. So the hydrogen bonds in water molecule make liquid water excellent at buffering the temperature. You guys should already know that because most of you are living in Western Washington, a few of you in maybe Western Oregon. And our temperature is buffered because of the water from the Pacific Ocean. And that's why our temperature in Washington and Western Oregon is milder than in Eastern Washington and Eastern Oregon. We have the water coming from the air as well as the Pacific Ocean, which buffers our temperature, meaning our summers are not as hot as in the east part of the state, and they're not as cold in the winter as the east part of the state because of the water buffering the temperature. Water absorbs a lot of energy, and this water can absorb energy in two ways. The water molecule itself can absorb the energy, in which case the water molecule will then move and vibrate faster. And what that means is the temperature of the water molecule increases. What the temperature is just the movement of the molecule. And if the water molecules are moving faster and more often, then the water molecule has a higher temperature. And if they're moving less, then the water molecule has a lower temperature. Anyways, the point is when you give energy to water, some of that energy can be absorbed by the molecules of water themselves, and then the molecules will vibrate faster, and that means the temperature of the water is elevated. The second way that water can absorb energy is some of that energy can be absorbed by the hydrogen bond. And that energy, if you give enough of it, will break that hydrogen bond. The point is that when you give like 1 cup of water, the same amount of energy as you give 1 cup of oil, the oil can only absorb the energy by absorbing it into the molecule, and then the molecules move faster. So 1 cup of oil for the same amount of energy will raise the temperature of the oil greater than it will raise the 1 cup of water, because we have two factors absorbing the energy in water. One being the molecule, which will elevate the temperature of the water, and then the second being the hydrogen bonds between the water molecules. Any question about that? So only a few things can do that, like water, where they have two things that absorb the energy, like a metal penny and oxygen gas. They only have one thing that can absorb the energy. And so they will raise in their temperature greater than water. And that there's only a few things similar to water where they have two things which can absorb the energy. Another thing about water which helps buffer the temperature is that when energy is absorbed by a molecule of water, that will break off the hydrogen bonds of that molecule of water, meaning that the molecules of water that have the highest temperature, they will be the water molecules that will evaporate from the body of water. So the hottest water molecules are the ones that leave the body of water. That tends to keep the body of water cooler. And that is why water is very good at buffering the temperature. And you guys do know this in a sense, and that is when you perspire or sweat, you're evaporating that water to help keep you cool. And the hottest water molecules on you will be the ones that will leave, and they'll take some of that heat with them. That will help keep you cool. Any question about any of that? All right. Water can split. So when H2O on the planet Earth splits, it splits into H plus and OH minus. Remember, H plus is the hydrogen proton, and OH minus is called the hydroxide ion. H2O on the planet Earth, with one exception, does not split into hydrogen ions and oxygen ions. It splits into H plus ions and OH minus ions. You would have to have water on the surface of the sun. You'd have to have that temperature, the surface of the sun, to split H2O into hydrogen ions and oxygen ions. And that doesn't happen on the planet Earth, with one exception. And that is you could take water and put in electricity and get the electrolysis of water. And we're not going to talk about electrolysis. Okay, that's a man-made invention in most cases, splitting water into hydrogen ions and oxygen. And that only happens on the planet Earth when you're sending the electric current through it. On the planet Earth, water normally breaks down into hydrogen ions and OH minus ions. The charged molecules of water participate in chemical reactions in the water and give the water its pH. Any question about any of that? All right, when we're talking about the pH, I'm showing you a pH scale here. Increasing acidity is where you have more hydrogen ions in solution than OH minus in solution. At neutral pH, when you have pure water and it breaks into hydrogen ions and OH minus ions, the hydrogen ion concentration will equal the OH minus concentration, and that we say is pH 7. When we have more OH minus ions in solution than hydrogen ions in solution, we have increasing basic conditions, and that's also called increasing alkalinity. And that's when the pH will be above 8. Below 7, the pH is, well, below 7. That's acidity. And this is showing you a pH scale. The most acidic thing that you actually probably know about around pH 1 is a car battery acid. The next most would be stomach acid around pH 1.5. And this will depend what you've eaten and how acidic your stomach is. If you have food that will buffer the acidity, the stomach won't quite be 1.5. It'll be higher than 1.5. Lemon juice around pH 2, grapefruit juice around pH 3, tomato juice and wine around pH 4, urine around pH 6, milk, pure water, and blood are all close to pH 7. Seawater is closer to pH 8. It's a little higher than pH 8. And that's from the dissolved minerals in the ocean, making the pH a little higher than 8. Milk of magnesia around pH 10. Household ammonia a little higher than pH 11. Household bleach around a little higher than pH 12. Oven cleaner is probably the most basic thing you've ever heard of or worked with, and that would be higher than pH 13. Lime water is really close to pH 14, and you probably never worked with lime water. An acid is a substance that dissociates, giving up one or more H plus ions in solution. Like if we dissolve HCl in water, HCl will dissociate into H plus ions and chloride ions, like this, and that will make the water more acidic. Why we call this hydrochloric acid. A base, your textbook will tell you, is a substance that dissociates, giving off OH minus ions. Like sodium hydroxide, you dissolve it in water, it will dissociate into sodium ions and OH minus. The OH minus will increase the OH concentration in the water, making this a basic solution. That's what your textbook author says, but I'm here to tell you your textbook author made a mistake or has an error, and a base is a substance that gives off OH minus, or a base is a substance that absorbs H plus ions, like bicarbonate, like sodium bicarbonate, baking soda in your kitchen is a base, and it absorbs hydrogen ions in water to make bicarbonate or bicarbonic acid, but bicarbonate. There we go, bicarbonate. The point is sodium bicarbonate or bicarbonate is a base and it absorbs H plus, and that's why a base can absorb H plus. Any question about that? By the way, this right here is one of the important buffers in your body. It is in blood. And if this can go both ways, by the way. And if you get your blood too basic, the bicarbonate right here, come on, mouse, will move this way. And then that will release hydrogen ions in your blood, as well as bicarbonate or whatever. And that will release acid in the blood to help neutralize the blood. On the other hand, if your blood is too acidic, the bicarbonate can combine with hydrogen ions in your blood to make bicarbonate. And I'm trying to remember what that's called. I'm just going to say sodium. Well, it's called sodium bicarbonate. I don't remember what the difference is between these two. There's a difference in their name, but this will happen in your blood to make this, and that will pull out hydrogen ions in the blood, making the blood less acidic. And the point is these two molecules are buffers in your blood to help neutralize your blood. Any question about any of that? All right, let's talk about salts and electrolytes. Let me end this. A salt is a substance that disassociates into cations, meaning a positively charged ion, and an anion, meaning a negatively charged ion, neither of which are H plus or OH minus. For example, sodium chloride, table salt, can dissociate into sodium ions and chloride ions, and this is a salt. However, magnesium chloride, which will dissociate into magnesium plus 2 and 2 chloride ions, is also a salt. Any questions about that? Electrolytes are substances that dissociate into ions in solution, and then the electrolytes can conduct electricity. For example, salt water is better at conducting electricity than fresh water. Any question about any of that? All right, organisms need to maintain a fairly constant balance between their cellular acids and their bases to remain healthy. And as I stated, we have this molecule and that molecule in our blood. And if our blood becomes too acidic, the reaction is driven this way. This will combine with hydrogen to remove the hydrogen ions from the blood to help neutralize the blood. And how that happens is something like when you're eating something that is acidic, like pickled foods or vinegar, or even a soda pop. The reason why you don't die when you drink soda pop is because you have this molecule in your blood which can neutralize the acid of drinking this soda. And then vice versa, when you eat, I don't know, certain vegetables are basic and the blood becomes basic, this molecule in the blood can break down into HCO3 with a negative charge and H plus with positive charge to increase the acidity of the blood. Any question about any of that? All right, the pH is a measure of the hydrogen ions in solution. The pH exactly is equal to the negative log of the hydrogen ion concentration. A log is just a scale, and then the hydrogen ion concentration is the pH. The pH scale runs between 0 and 14 on a log scale. pH 7 being where, well, let me go through that exactly. pH equal to, you can get that right. Oh, I hit the wrong button. pH equals 7.0. We're just going to go there. This equals, let me blow that up a little. This is equal to 1 times 10 to the 7 H plus, oops, ions. I don't have that right either. So this is 1 H plus ion. See if I can do that. Not here. One H plus ion in 1 times 10 to the 7th water molecules. That's what pH 7 means. pH 8 is 1 H plus ion in 1 times 10 to the 8th water molecules. And pH 9 the same. That makes sense? And then for the acids, pH 6 is the same. Is 1 H ion in solution for 1 times 10 to the 6 water molecules. So that would be 1,000,000 water molecules. There's 1 H plus ion in solution if the pH is equal to 6. Any question about any of that? Come up here. Oh, we have half an hour still. Okay, good. So acid is where the hydrogen ion in solution is greater than the OH minus. Basic or alkaline solution where the OH minus in solution is greater than the H plus. Most organisms grow best around pH 7. So most grow best between something like pH 6 to pH 8. Any question about any of that? All right, if not, let's talk about organic chemical compounds. You're seeing organic chemical compounds here. Some of them can be fairly complex, like this one here and these here. You do have a few organic compounds which are simple. This is the simplest one, acetic acid, which is, I believe, vinegar. And I guess the simplest, that's not the simplest. This is the simplest, methane right there. Organic compounds always contain carbon and hydrogen. Oftentimes they contain oxygen, but they don't have to contain oxygen. And they may contain other molecules as well. Let me see if I can blow this up. So if they contain oxygen, I'll bring this down here. There may not be much oxygen in the molecule. Like this one here. Well, that's not bad, 2 out of 2. But this one here, most of these molecules are carbon and hydrogen, carbon and hydrogen. And there is some oxygen, but there's only 2 right there and 2 right there. And this we'll talk about later because let's just remove that. This is a phospholipid and we don't want to talk about a phospholipid right now. So we're only going to talk about this part of the molecule. Yep. Organic compounds always contain carbon and hydrogen. Many of them contain oxygen, but not all organic compounds do contain oxygen. They may contain other elements like nitrogen, sulfur, phosphorus. All of these different atoms are held together covalently by an organic compound. Compared to inorganic molecules, they are more complex and they're capable of more complicated biological functions. Some examples of organic compounds include carbohydrates, nucleotides, lipids, and then various hydrocarbons. What a hydrocarbon is an organic compound that is only composed of hydrogen and carbon, like methane, ethane, and propane are all hydrocarbons. Any question about any of that? What's unique about organic compounds is that they tend to be held together by carbon. Carbon can hold or bind to 4 other atoms. Carbon can be bonded together in a chain or a ring structure. So here we're looking at a linear structure. Let's go back here. And this would be the chain or the ring structure. And that's the linear structure. What's holding these atoms together are chemical covalent bonds. The carbon skeleton is the backbone of an organic compound. So right here, the carbon skeleton are the 3 carbon atoms being held together. And let's look at this one here. What's holding this molecule together, not this part here, but this molecule together, is almost entirely carbon backbone. The only exception is there and there. So the carbon skeleton tends to be the backbone of an organic chemical molecule, holding the molecule together. We can have functional groups bound to a carbon backbone. These chemical functional groups influence the chemical behavior of organic compounds. Right here, we're seeing methanol on methane. The functional group, the OH group, gives this molecule different chemical properties than this molecule, methane. For example, methane is a hydrocarbon. It's a gas. It doesn't dissolve well in water, meaning it's a polar molecule. No, excuse me, it's a non-polar molecule. Methanol, on the other hand, is a liquid, and so it dissolves well in water because of this OH group. And obviously it's not a gas. And the point is, the only difference between methane and methanol is this functional group. Any question about any of that? All right, the functional groups are responsible for most of the chemical and physical properties of a particular organic compound. Hydroxyl groups, the OH group, is a group found in alcohols. It is hydrophilic. Why methanol dissolves in water? Because the OH is hydrophilic. The methane is hydrophobic. Where do I have methane? Right here. Methane is hydrophobic. And that OH group helps the molecule dissolve in water or in alcohol. I think that should be in water, but we'll take a look there. It does dissolve in both because methanol is an alcohol, so obviously it can dissolve in alcohol. Here are the different functional groups you need to know about. The one surrounded by a red box. You need to know OH group, which is found in lipids and carbohydrates, and it's not stated here, but it's found in nucleotides as well, or nucleic acids as well. You need to know the amino group, the NH2 group. It's found in proteins and amino acids. You need to know the carboxyl group. It's found in organic acid, in lipids, and then proteins and amino acids. And a carboxyl group is COO, with that O being a double carbon bond, and then this O being a single carbon bond, and this O has an H on it. So this is an OH group. And then the last group you need to know about, or functional group you need to know about, is the phosphate. And it's PO4 with a negative charge. Phosphate is found in DNA, RNA, and ATP. Any question about any of that? Frequently, more than one functional group can be found in a single molecule. For example, all amino acids are shown below have both an amino group and a carboxyl group on the amino acid. Any question about any of that? Okay, when we're talking about organic compounds, it's important to realize that we have macromolecules, which are big organic compounds that can be made up of smaller molecules. And you can simply combine the small organic molecules to make the macromolecules. The macromolecules in biology are called polymers, consisting of many small repeating molecules that we call monomers. So many, well, actually all of the polymers are made up of monomers. An example of that is starch is a polymer, and all it is repeating monomers, which are glucose. Any question about any of that? All right, organic compounds can be created by dehydration synthesis. And another word for dehydration synthesis is condensation reaction, where you can combine two monomers, ROH. The R just stands for anything, and then HR are the two monomers, and the H comes off of this monomer, OH comes off of that monomer, and in condensation reaction or dehydration synthesis, this R will now bind directly to that R, and then water comes off as the H and the OH come together to form water. Why it's called dehydration synthesis: in the synthesis of the RR polymer, we also make water. I think that's why it's called condensation reaction too, and that is water condenses out of this reaction. The reverse molecule, where you take the polymer and you add in water, you split the water, and then the hydrogen comes to this R, the OH of water comes to this R, and this is called hydrolysis, where you split the polymer by water. And usually when you split a polymer, you break off one monomer. And so this would continue being the smaller polymer. And I think I've got a better picture in the next one. Yeah, right here. Add the water that splits off this monomer, and then you have a smaller polymer right here. Let me state that you are familiar with hydrolysis, assuming you've seen the movie Back to the Future. And when Marty McFly says to his Ma, "Ma, you sure know how to hydrate a pizza," she took this hockey puck-like structure and put it in her pizza hydrolysis machine and turned it on. And lo and behold, the pizza hydrolyzed and this beautiful pizza came out. And that was by the hydrolysis of the pizza. Any question about any of that? All right, so once again, dehydration synthesis, you get a monomer coming together, in this case, with a polymer, a smaller polymer. The hydrogen comes off the polymer, the OH comes off the monomer, water will form from the hydrogen and the OH coming together, and then that monomer will directly link to the polymer. The reverse reaction I've already talked about, you add the water, you split the monomer off from the smaller polymer. The point is that dehydration synthesis and hydrolysis are the reverse of each other. All right, any questions about dehydration synthesis or hydrolysis? If not, let's talk about the four biological molecules. First, we're going to talk about carbohydrates. These include sugars, starch, and other complex carbohydrates. They are important energy sources for people and living organisms. You can find carbohydrates in the structure. You can find carbohydrates in nucleic acids. Carbohydrates always consist of carbon, hydrogen, and oxygen, but not just in any general formula. They only are found in this specific formula, where for each carbon, there are two hydrogens and one oxygen. So for a carbohydrate, you can simply go CH2, put it in parentheses, and then put an N, and you'll have whatever the N is for that many groups in the carbohydrate. For example, with glucose, it's CH2O in parentheses, and then the N is 6. So the glucose is C6H12, or H2 times 6, 12, and then O6. Any question about that? All right. Simple sugars or strings of simple sugar are linked together to make the other carbohydrates. And we can classify carbohydrates into three major groups based on their size. You have the monosaccharides. They are the monomers of carbohydrates. You have the disaccharides. Oh, mono means one, by the way, one saccharide. Saccharide means sugar. Disaccharide is two sugars. Di means two saccharide sugars. An example of a monosaccharide is glucose and fructose. An example of a disaccharide is lactose. I used to know this, and maltose. I used to know that all the disaccharides. I'm having a hard time remembering another disaccharide, lactose. I'm drawing a blank for what maltose is, glucose and glucose. Lactose is beta-galactose and glucose. I don't remember the other disaccharides. Okay.
Isn't sucrose a disaccharide?
Yeah, there it is. That's the one I was trying to think of. What's the name of sucrose? Table sugar. And that's fructose and glucose hooked together. All right. Thank you. Polysaccharides are the complex carbohydrates. The simplest polysaccharide is starch, and it's simply glucose linked together one after the other in a simple chain. And the glucose is simply the monomer. And starch is the polysaccharide or the polymer. All of the complex polysaccharides are the polysaccharides. Let's take a little look at some monosaccharides and disaccharides. Monosaccharides are simple sugars. All of them are between 3 and 7 carbon atoms, but usually monosaccharides are either 5 or 6 carbon molecules. All the monosaccharides are sweet. They're all water soluble. Here we go. Disaccharides are formed by joining two monosaccharides together in dehydration synthesis. So you can take glucose, C6H12O6, and you should know that, by the way. Fructose is also C6H12O6, but fructose is in a different structure than glucose, as shown here. And then you pull out the OH group from glucose, the H from fructose, and then link directly that oxygen to that carbon right here. Oxygen bound to this carbon in dehydration synthesis to make sucrose. And then water is formed. And then to do the reverse, you take sucrose and you add water. Water will break apart, part of it going to the fructose, and that'll be the H to the fructose, and the OH minus to the glucose to have hydrolysis. Any question about any of that? All right. I already mentioned polysaccharides consist of many monosaccharides, many monomers. They can be straight or branch chained molecules. Starch is mostly, not entirely, but mostly simply glucose hooked together one after another in a linear simple chain. Although this can be a very long chain, but that's what starch is. Starch can be branched, but doesn't branch very often, and mostly it's non-branch like this. Here are some examples of some starchy foods: starch, bread, cereals, pasta, rice, potato. Everybody knows these are starchy food. A lot of people don't know that beans and chestnuts are starchy foods too. And beans do have protein. They even have lipids, but they are about a third starch. And beans are actually about a third carbohydrate, a third protein, and a third lipid or fat. Chestnuts are similar, although I don't know the makeup of chestnuts. I think I show glycogen here. So starch right there. All it is glucose hooked together, one after the other. So each of those dots is a glucose. Glycogen is very similar. It's hooked together by glucose, one after the other. Glycogen is the way our muscle cells and heart, what else? Liver store glucose. It's very similar to starch, except that this chain is branched. So right here, it's linear and then it branches into two, and then that branches again into two more. Cellulose, we'll talk about it in a little bit. Let's see if I can blow this up. You have to blow it up real high to see. Cellulose, there, you can see it now. Cellulose, once again, it is simply glucose hooked together one after the other. It is a different length than in starch. But what makes cellulose so different is here is one strand of cellulose, and there's another strand and a third strand. And cellulose has a lot of hydrogen bonding between the cellulose. So this glucose will have hydrogen bond to this glucose over here and to that glucose over there. This glucose here and that glucose there, that's a covalent bond. So wherever you have a blue bond, that is a chemical covalent bond. The dashed yellow and brown is a hydrogen bond. I can mention that cellulose is something that most animals cannot digest. It is used in plants to help give them structure. And I assume plants have a lot of cellulose because they know that animals can't digest it. And for example, humans would never eat grass because we can't digest it. Cows can, but they don't digest the cellulose. What they do is they have a microbe, and actually that microbe has bacteria and archaea in its gut uh, to digest the cellulose. So in reality, you've got the cow who has a microbe, and I used to know the name of that. Um, it's not an insect. What the heck is that called? Anyways, it has a microbe in it that has bacteria in it, and the bacteria can digest the cellulose. And that's how the cow can eat grass and digest it. Not because of what the cow can digest, but because of what its microbe can digest. Chitin, I'm not going to talk about. We'll talk about peptidoglycan a little bit later in the term. For now, you just need to know that peptidoglycan does have, well, it is a partly carbohydrate, and that it is linked together by monomers of sugar. We're not going to talk about what type of sugar now, we will later, but it is linked by simple sugars, one after the other. And it's linked by a few other things, which are not a carbohydrate, and we'll talk about that later too. But peptidoglycan is considered at least a part of a carbohydrate, if not entirely carbohydrate. Any questions about any of that? All right. Lipids are our next biological molecule we want to talk about. They consist of carbon, hydrogen, and oxygen. And although lipids do have oxygen in it, there is not much oxygen in a lipid. Let me blow this up. I think you can see it there. So this is a fat, and not a fat, a lipid, and it has a very long hydrocarbon chain right here, and it does have oxygen right there, and then this will come off, but it does have OH right there. So the point is there isn't much oxygen on this fatty acid, which is a component of a lipid. When we're talking about fatty acids, it's important to realize that we can have a saturated fatty acid, which is shown here. A saturated fatty acid has all of the carbons linked together by a single carbon covalent bond, meaning all of these carbons here are linked to each other by a single carbon covalent bond. An unsaturated fatty acid has at least one double carbon bond linking the carbons together. And I'll show that here. Let me blow this up a little. There you go. So this hydrocarbon only has a single carbon covalent bond linking the carbons together. Same with this one. But this one here has one double carbon bond, where there are two covalent bonds linking the carbons together. Wherever there's a double carbon bond, you'll get a kink in the structure of the molecule, in this case, a fatty acid. Any question about any of that? Let me go back to make sure I talked about everything. Yep, I did. All right. All right. So let's talk about simple lipids. They're also called fats or triglycerides. Triglycerides are the most common fat in the human body. And if you want to look at some triglycerides, just look at your belly. There's usually lots of triglycerides there, even if you're thin like me, because we store a layer of lipid underneath our skin in our belly. At least humans do. Fats contain a fatty acid, which is shown here. I guess I never said that. That's a fatty acid. And one glycerol. So here's glycerol. It's this molecule here, the brown part here. And there's the fatty acid. The fatty acids can come together with glycerol to make a triglyceride. And a triglyceride just means three fatty acid, 1, 2, 3, hooked to glycerol. And this is a triglyceride. Tri means three. And like I said, it's the most common fat in your body. I guess I should say that this triglyceride is considered unsaturated because it has one double carbon bond in the triglyceride. You only need one, and you're considered unsaturated. So even though that's totally saturated, we say this triglyceride is unsaturated. And a triglyceride contains 3 fatty acids linked together with glycerol. Triglycerides are the richest energy source, stored as adipose in animals. If you need a lot of energy and you have to carry it, and you're trying to figure out what molecule of food should I carry to give myself the most energy, you would want to bring or carry a bunch of triglycerides, meaning fat, because you get the most energy per gram out of 1 gram of fat or lipid than 1 gram of any other food you can eat. So it's the body's richest energy source. And let's say you're in Point Barrow, Alaska, driving around in the wintertime, and you don't have a coat on because you're using the heater in your car, and your car breaks down, and you're got to hike into the city or the town, and it's 20 miles away or further, and you got to walk that way, and you're wondering what can I carry to give myself energy to get to the town. And like I said, the best thing to do would be to carry something that is a fat or a lipid, because you'll get the most energy out of it. All right, moving on to our different types of lipids, we have a phospholipid, and it's a very unusual lipid. A phospholipid is a lipid that is 2 fatty acids right here and right there, bound to a glycerol right here. But in the third position, we don't have a fatty acid because that would be a triglyceride. We have a phosphate molecule, and this we call a phospholipid. You should note that phospholipids are unusual among lipids because they have a polar region. The phosphate group is polar. The glycerol is slightly polar, about it's not much polar, but it is slightly polar. And then a nonpolar region, the fatty acids are nonpolar. Any question about any of that? That makes phospholipids unusual for a lipid because they are biphasic. They can dissolve in both water and in oil or lipids. So a nonpolar molecule can only dissolve in oil or lipids. It will not dissolve in water. And then a polar molecule, or ionic, can dissolve in water, but would not dissolve in lipids. Phospholipids can dissolve in both because it is a biphasic molecule. When you have a bunch of phospholipids together, they will start forming this structure in water, and I'll talk about that a little longer and a little bit in the next slide. The phospholipids are the main part of the cell membrane of eukaryote cells and bacteria. Oh, I'm a little bit beyond that. Let me end here. Are there any questions? All right, if there's no questions, I'll end it here. And I will see you at 7 for the lab, for those of you who are coming to the 7 p.m. lab.
Thank you.
Thank you.
Thank you.
Thank you.